In this video, we're going to continue our discussion of ionization energy. So we said that the ionization energy is the amount of energy required to remove the outermost, most loosely bound electron from an atom in its gaseous state in its ground state. The first ionization energy is the energy required to remove the outermost electron from the neutral atom, in which we form a cation with a +1 charge. The second ionization energy, of course, would be the energy required to remove the second most loosely bound electron. And in this process, we start with a +1 cation and we end up with a +2 cation. And of course, we can have a third, fourth, fifth ionization energy as well. The ionization process always requires energy to remove an electron. So this is called an endothermic process. The smaller an atom's ionization energy, that means the easier it is to remove an electron and form a cation. So the smaller an atom's ionization energy, the less energy it takes to pull off that outermost electron, the more readily it will form a cation. Removing an electron from a cation requires more energy than removing an electron from a neutral atom. Put another way, an atom's first ionization energy will always be less than the atom's second ionization energy. So pulling the first electron off the neutral atom requires less energy than removing the second electron from the +1 cation. And it follows that the first ionization energy for an atom requires the least amount of energy. Then the second requires a little more energy. Removing the third electron requires more energy. The fourth electron, even more energy, etc., etc. So why is that? Why does it require more energy to remove the electron from a cation than a neutral atom? Well, of course, a cation for an atom has a greater effective nuclear charge when compared to the neutral atom. If we pull an electron off of an atom, we haven't changed the protons, so the actual nuclear charge remains the same. But we did remove an electron, so therefore the shielding decreases. So the effective nuclear charge for the cation is greater than the neutral atom, meaning that the cations the electrons in the cation are going to feel a greater attractive force towards the nucleus, making it more difficult to remove. So the more positive the cation, the more energy required to remove the next electron. So as we said before, removing an electron from a neutral atom requires some energy. A +1 cation, more energy. A +2 cation, even more energy, etc. So pause the video for a minute and look at this chart. This chart shows the ionization energies, the first, second, third, all the way to the seventh ionization energy for our elements in the third period. Pause the video for just a minute and take a look at this chart and see if you see a trend. Okay. So here, looking at our elements, here we have them for the third period. Sodium's first ionization energy is fairly low. In other words, it's very easy to remove the electron from sodium. And then the second ionization energy, there's a large jump. It increases by almost tenfold. For magnesium, the first electron comes off relatively easy, doesn't require a lot of energy. The second requires a little bit more energy, but then there's a big jump from the second to the third. Again, you can see that around 6 or 7 times the increase. Aluminum, the first ionization energy is relatively low. The second requires a little more energy, third a little more, and then again you see a big jump between the third and the fourth. And this trend continues on down for silicon, phosphorus, etc., etc. So why is this trend the way it is? Well, we need to look at the electron configurations for these atoms. Here we can see the electron configuration for sodium. Sodium has only one valence electron. So the first ionization energy, we're removing this outermost valence electron, and that comes off very easily. The second through the seventh ionization energies, we would be removing core electrons. Those core electrons we know are going to be held much, much more tightly to the nucleus because they experience a much greater effective nuclear charge than this outermost valence electron. For magnesium, we can remove the two outermost valence electrons relatively easily, and you can see that here. But when we go to the third electron, there again we're removing a core electron. So there's going to be a big jump in the ionization energy because those core electrons experience a very great effective nuclear charge when compared to the valence electrons. And again, for aluminum, we can remove the first three electrons relatively easy. They don't require too much energy because they're valence electrons and they experience a relatively weak effective nuclear charge. After that, the fourth through seventh ionization energies for aluminum, we would be removing core electrons, which experience a very large increase in the effective nuclear charge. And you can see that trend on down. So be sure that you can explain that trend in terms of effective nuclear charge. So just to sum it up, valence electrons are easier to remove because they have in other words, they have a lower ionization energy than core electrons. The valence electrons experience a lower effective nuclear charge, whereas our core electrons experience a much greater effective nuclear charge, making them harder or requiring more energy to remove. So be sure you can understand the trends for first, second, third, fourth, fifth ionization energies for a given atom.